Speakers are Connor Galloway from Innoven Company in the US and Mike Tobin from the Johns Hopkins Applied Physics Laboratory. So they will share the talk in the following minutes. Okay? So please, Connor.
Okay. Hey, my name's Connor Galloway, and I'm the chief scientist at Innoven Energy. Innoven is a United States private company, and our team, members of our team, have been involved in laser research, fusion research, optics research since the mid-1970s and on. And more recently, in the past 10 years, at Innoven, we've developed a new laser architecture for ICF that's quite different from all previous architectures that have been proposed, and which we believe make a major contribution, a major step towards achieving commercial IFE in the long run. And so I'm excited today to tell you about our ideas and our approach to laser for ICF. So what is needed for a practical IFE driver? So these are kind of our starting assumptions. Low cost, high single pulse energy, as you heard from Mike Campbell, going up in energy, 10 plus megajoules increases the confidence that you can achieve ignition and high gain. High fluence, what this allows is small solid angle subtension of the final optics, which reduces engineering requirements for a reactor. High optical quality, you want uniform illumination of your targets. And high driver efficiency. So here we have 5% or higher. And of course, this has to be balanced with target gain. At lower driver efficiency, you need higher target gain. Mike Campbell just discussed that. And the ability to ultimately reparate the system for power production. So many of you are probably familiar with NIF. You've heard about it in prior talks. This is a glass laser architecture, and the way it works is it starts with a nanosecond scale pulse and then amplifies that in the glass media up to full energy. There are a few drawbacks to glass. One, it's limited in fluence to 5 to 10 joules per square centimeter. It's easy to damage, it's expensive, as you've heard before, and it has a high nonlinear index, which means it's harder to maintain good beam quality as the pulse propagates through the system. So our approach is kind of opposite. We start with a very long pulse, 3 microsecond duration from a Caref laser amplifier. And then we first spatially compress it in cross-section to high fluence. Then we temporally compress it from 3 microseconds down to 1 nanosecond. And then we image the light on the target. And this imaging amplifier, the way it works, and I'll discuss later, is that a low energy pulse is imaged on the target, the rays leave the final optic, and then they're amplified to full energy after the rays leave the final optic. So in more detail, the Caref laser amplifier, it's electron beam pumped excimer gas laser, and it's low cost and high energy. And this low cost and very high energy is achievable by going to very long pulse lengths because the pulse power simplifies. And our estimates are we can build a Caref laser amplifier at under $8 a joule optical output. The aperture combiner is effectively beam combination to high fluence. We go up to 1,800 joules per square centimeter. So this is far above material damage thresholds. It's, a lot of energy through a small area. And this is done using stimulated Ramon scattering, which I'll talk about in detail. So you can effectively think of it as a gas mirror. Next, we then pulse compress 3,000 to 1 in time from 3 microseconds to 1 nanosecond. And again, here we use stimulated Brion scattering. This also effectively acts as a gas mirror in addition to a pulse compressor. And then finally, as I mentioned before, we image the light on target and then amplify that light after it leaves the final optic. Okay, so our kind of motto is gas, not glass, because it's inexpensive, can't damage it, and it can handle much higher fluence than glass can. And ultimately, this is how we can have, because we have 10,000 times less high-quality glass per volume than an equivalent glass laser, such as NIF, that's how we can achieve such low cost, such a dramatic cost reduction. So the content of this talk, first I'm going to talk briefly about our Caref amplifier, and then what is stimulated scattering, how can it be used to replace material optics. Then I'm going to go through the detailed operation of the Aspen laser architecture, how it works. Then discuss a key experiment done by our team in the past that's relevant to the operation of the Aspen architecture, and then dive into some of the physics basis for SBS pulse compression. And so this last point is really the key. Our key innovation is how we can compress from 3 microseconds, which is very long, relevant for ICF, down to 1 nanosecond at high fluence and good enough efficiency. Okay, so Caref Basics. So as Mike Campbell had mentioned, Caref is pumped by pulse power. So you have a pulse power system, in our case a Marx generator, and a high voltage cathode. This is like a diode. And when the diode discharges electrons through the hibachi into the gas, it excites the gas, and then you inject a seed beam laser at low energy into the one end of the amplifier, and it extracts light at 248 nanometers as it passes through. So this is a engineering schematic of our amplifier. So this amplifier is rather big. The output area is 3 by 6 meters. It's 12 meters long, 3 microsecond pulse length. So this is much longer than other current Caref efforts, such as like at NRL. High output energy, high output fluence, so 14 joules per square centimeter out. And this is not going to damage windows or optics because we're at such long pulse length. You know, it's not at a nanosecond pulse length here. 1 pressure gas, diode voltage 2 megavolts, and the diode current's 11 amps per square centimeter. So compared to current efforts, other efforts pursuing Caref, big amplifier, high voltage but lower current per area, lower pump rate. The Caref gas here is pumped at 55 kilowatts per cc. The pulse power is a Marx generator in a pulse forming network. No electrical pulse compression is required because we're at 3 microseconds. We do all the pulse compression optically. And our estimated hardware cost is, again, $8 per joule output at 3 microsecond pulse length. Of course, in the long run, to have a viable IFE system, you have to rep rate the system. And so we envision this operating at 1/4 hertz to a hertz, or below 1/4 hertz, depending on exactly where the target design that's chosen in chamber and how everything's optimized together. But the 3 basic things that are needed to rep rate an amplifier like this are vertical gas flow and cooling. You have to flow Caref gas through the chamber to cool it. If you're lower rep rate, flow velocity is lower. You have to cool the Marx switches that trigger when the Marx erects, and then capacitor cooling and lifetime. And we're currently working with pulse power experts at LLE. Still a lot of work to do, but the initial assessment is that this can be readily doable at 1/4 hertz operation with current technology, but if you try to push a hertz or higher, there'll be significant engineering challenges. So again, a lot of work to do here in the future. Okay, stimulated scattering, gas mirrors. So before we talk about stimulated scattering, I want to tell you about spontaneous light scattering. So shown here is incident light enters a scattering medium. It's going to scatter in all directions. You're probably familiar with Rayleigh scattering, why the sky is blue. So over here is kind of the scattered intensity of light as a function of frequency. So Rayleigh scattering is light that's scattered, but the frequency doesn't change. However, you also see here a Brion and Ramon scattering where you have frequency shifts, where the scattered light is upshifted or downshifted in frequency relative to the instant light. And the mechanism for this, the classical picture, here's equation, you see the polarization equal to the electric field of the instant wave times a modulation in the electronic susceptibility of the medium. So for Ramon scattering, you can imagine molecules vibrating or rotating, and the vibration or rotation will modulate the electronic susceptibility of the medium. And so if you just form complex exponential product of e to the omega, and you I omega, and then you have another complex exponential at omega r, corresponding to resonance of the molecular rotation or vibration, you get your output up and down shifted, your polarization, which sources the scattered wave. The quantum picture for Brion scattering on the right is an incoming photon scatters off of a phonon. And then for Ramon scattering, you can imagine first absorbing the initial photon, going up to an excited state, then de-excites to a higher level, higher excited state level in the molecule, and the frequency difference between the ground state or first bottom state and excited state is equal to the Ramon shift. So stimulated scattering. So here we have an interaction medium, which is a Ramon or Brion active medium, and you have pump light coming in at nominal frequency omega p, and now you purposely inject what's called a seed beam or Stokes beam coming in at the frequency offset, at either the Ramon or Brion offset. And when you do this, you have the seed beam will amplify via stimulated scattering, and the pump light will deplete. And these equations govern the process. And you can just see here that the pump light has a negative sign there. It depletes as it moves along, and the Stokes or seed beam light amplifies as it moves along. And this process is governed by what's called the coupling constant, which is the gamma there. And that's typically units of centimeters per watt. and it's determined by the material properties, what gas it is, pressure, et cetera. So the classical picture, which is quantitative for SBS, is that you can imagine the pump light and the Stokes light, they're at a frequency offset, so there'll be a beat wave. That beat wave, if it matches an gas acoustic wave at frequency omega, it can increase the amplitude of the fluctuation via electrorestriction. And then the larger fluctuation will then scatter more pump light into the Stokes light. And it's a feedback mechanism, so the seed light at the Stokes frequency amplifies, the pump light depletes. And the quantum picture is pretty straightforward. You have this MS plus 1. The MS is stimulated emission, and the 1 is spontaneous emission. This is analogous to stimulated emission and atomic transitions. Okay, how can we use this, make use of stimulated scattering? Well, the first application is what's called beam combination. So this is when the Stokes and pump are in the forward direction. So here you see a seed beam entering an interaction medium, and you have pump beams coming through, and the seed beam amplifies, comes out at higher energy, higher fluence, and the pump pulses deplete. On the right, there's pulse compression. So here, now the beams are counterposed. So you inject the seed beam right to left at short pulse, and the pump pulse comes left to right at long pulse time, and the seed beam extracts energy from the pump and comes out carrying a large fraction of the energy, so you have effective pulse compression. Specifically in the Aspen architecture, we use rotational into Ramon scattering in atmospheric air for the Ramon interaction medium for beam combination, and we use Brion scattering in noble gases at 1 atmosphere pressure for pulse compression. I'm going to talk about that in more detail later on. Okay, so how does the Aspen laser architecture work? So this is an illustration of the system at a high level. In the upper right, you see the Caref amplifiers. They emit light. It comes down here and to the region where you have optical energy compression. So this is where there's spatial compression to high fluence, and then temporal compression to 1 nanosecond. And then finally, you have optical energy on target. So to depict this is a high-level schematic. And so here's kind of color-coded to optical energy generation, compression, and then to target. And the main Lego blocks, or components of this architecture, the large pump module, you have what we call the aperture combiner. That's where the beam combination is going to take place. Fast compressor and direct compressor are 2 separate independent pulse compression stages where the light's going to go from 3 microseconds to 30 nanoseconds, then 30 nanoseconds to 1 nanosecond. So this depicts the operation here. Here you see the output from the Caref amplifiers directed to the aperture combiner, and the seed beam is injected right to left from a seed beam laser shown there, depicted there, and it amplifies up to 18 megajoules, and this light is at 1800 joules per square centimeter and occupying a 1 square meter beam. So very high fluence, a lot of energy through a small area now. Okay, the next step is you have another seed beam generator here. So you inject another seed pulse at really low energy from left to right, and the pulses counter-propagate, and you have energy transfer from the long pulse to the short pulse. And the output of this section is 16 megajoules. Fluence is now 1600 joules per square centimeter, same 1 square meter beam size, and a 30 nanosecond pulse. And then the second pulse compression step is depicted here. You have a third seed beam coming from a laser system over here that's injected. And again, the pumps cross at a shallow angle, but still near backward direction. And you get 12.2 megajoules out at 1660 joules per square centimeter in a 1 nanosecond pulse. And so this is depicting the energy influence and size of a full beamline of the Aspen architecture, which can put 12 megajoules to target. So this is an animation of the process to make things more clear. Let's hope it plays if I click the next button here. Yes, okay. So here you see first a seed beam laser that goes through the amplifiers. The light then amplifies and the outputs the full pump energy at 3 microseconds. Now you see forward beam combination. The seed pulse is amplifying, extracting pump energy, and then coming down this long, what we call direct compressor pipe at high fluence, at still 3 microseconds. Then another seed pulse at 30 nanoseconds is injected, counter-propagating to it. It extracts energy from the pump through stimulated Ramon scattering. And it comes back. Now the back end of the 3 microsecond pulse is traveling here. And you'll see at the very end, a final seed beam pulse comes and extracts energy from the purple pulse and takes light to target in a nanosecond pulse. So this is a depiction of kind of the final section, the fast compressor. So here you have a final optic. The final optics in this system are 25 square centimeters. There's a beryllium mirror there, polished beryllium mirror. That's to protect the final optic from neutron damage. That'll be coming back from the target in a reactor. Then there's an active region. This is filled with neon at atmospheric pressure, noble gas. There's a shutter, which will open and close on each shot. Again, we're intend to operate at low rep rate, a hertz or under. So, and everything's at atmospheric pressure, so there's no pressure gradient. So shutter opens, shutter closes for a shot to pass through. Then helium is a buffer gas, and then there's a vacuum transition section. What this is it's a shutter and a flange that will open on a shot, and the shutter will close, and the flange will close, and you'll lose under a cubic meter of helium, well under a cubic meter of helium into the chamber. But you won't. The system will actuate, and you won't get rarefaction coming back to the neon where the pulse compression, final pulse compression is happening. So down here you see, and this is to scale. That shows you at 5 meters. So this final section is not that big in physical extent. And down here, this just depicts the pump pulse. So the seed pulse will come in, go to target, and it'll cross the pump pulse coming back and extract energy from it. Okay, this is another diagram depicting that. So you have a seed pulse come in from a front-end laser, low fluence, it's imaged on target, and the final optic of the imaging system that's projecting the pattern you want on target is there. And the fluence is about 1/4 joule per square centimeter, so very low fluence. The light then comes off the beryllium mirror and then immediately enters the active region where it's pumped. And it amplifies 10 to the 4 in energy to carry a megajoule to target for this one 25 square centimeter optic, as you can see here. So there are 2 key factors here to this in order to achieve uniform illumination of the target in this method. One is that, which I'll discuss shortly, is that amplification of the seed beam is not affected by the beam quality of the pump pulse coming through. The pump pulse can have some intensity variation, maybe slightly non-uniform, but it impresses no phase perturbation on the seed pulse as it comes through, and that's critical. Second, the nonlinear index of the active media and the helium buffer gas is very low of neon and helium, and we'll see later a comparison to glass, very, very low. So you can pass very high fluence and high intensity through it without affecting your ability to image the light and introducing significant non-uniformity. So this is a depiction, a very high-level, simple depiction of the last section. You see the seed pulse coming in from one module, that's 25 square centimeter. It hits a phase plate. The phase plate impresses a phase perturbation on this light. And this light is at, the seed pulse needs to be at high beam quality, high spatial coherence. The rays then leave the lens, and then at focus of the lens, which is where the target is, the phase perturbations impressed onto the light turn into intensity perturbations on target. And so the pattern on target is determined by the phase plate. And you can see here that it's very low fluence on the phase plate, but you get a megajoule on target. And so what's key here is we're amplifying the light after the final optic, after it's imaged on target, through a medium with very low refractive index and nonlinear refractive index. And we estimate that for these reasons, we can achieve 1% to 2% RMS illumination on a target, and the feature sizes are set by the diffraction limit of the system. Additional patterns are possible, depending on the phase plate, ring of light, indirect drive, spot array if you want indirect drive with a bunch of spots, or a disk of light if you want to do direct drive. And shown there is a picture of this from an experiment in 1990 related to astronomy, where a phase plate was used on a uniform beam to impress a phase perturbation, which turned into an intensity perturbation 10 kilometers up into the atmosphere. And this was used for guide stars for atmospheric compensation in this experiment. But this just shows this in action, this process. Okay, so finally, a full beamline is composed of 12 of these 1 megajoule modules, which I was just showing. So each 1 megajoule module is 25 by 25 centimeters. A full beamline has 12 of them put together in a 3 by 4 array. And they're all imaged, the image plane overlaps on target as shown here. This is a little animation showing actually how the pulses cross. So what you see here is the seed pulse that's imaged on target, and you see the pump pulse, which is coming back through the direct compressor at 30 nanoseconds. And you see the pump pulse is actually staggered in time, so it's not one big optic, it's 1 square centimeter. It's several smaller optics, and there's time delays on each one, just path length time delay, such that you stagger the light in this way so you have efficient overlap between the seed and pump pulse. Now this is a top-down view, so this is as if you're looking at the system from the top looking down. Now of course for many targets, you want more than one pulse of light. You want to be able to do multiple pulses. And so the Aspen architecture can readily achieve this. This is a depiction of this. So this is showing the seed pulse and the pump pulse. Looking at the seed pulse, looking down would be looking down this way. You see the 3 apertures across and the 4 stacked. And what you do is you simply time delay the seed pulse coming into, in this example, the top 9 apertures. Time delayed by whatever time you want, nanosecond, 2 nanoseconds, depends on the target design. And so in this case, you have a first pulse at 1/4 of the total energy, and then a second pulse that comes later, 3/4 the total energy. But of course, you also have to time delay the pump pulses coming through the system. So you can imagine looking down onto the system, you see that staggering for efficient overlap, where the arrows are shown there, but you also see this time delay of the bottom slab of light compared to the top 3 slabs. And you have the time delay of the pump pulse to match the time delay of the seed pulse. And this is the only thing you need to do in order to get 2 effective pulses. You don't have to time delay the beams, the seed beams back up in the architecture. That's driving the direct compressor or the output of the Caref amplifier. In addition, these are separate phase plates and separate optics. And so the bottom 3 phase plates can make one pattern on target, and the top 9 phase plates can make a different pattern on target. And so this connects to the hybrid target that Mike Campbell mentioned, where first pulse is indirect drive, you want to hit baffles on your whole ROM. Second pulse is direct drive, where you hit the target at, after it's been driven partly by a first shock. So this just shows an overall summary of the architecture for a full beam line. 20 megajoule output from 4 Caref amplifiers, like the ones I showed you at the beginning. Then 18 megajoules out of the aperture combiner, 16 megajoules out of the direct compressor, 12.2 on target. And you can see here that as soon as you go to the aperture combiner output, we're at high fluence. We're at 1800 joules per square centimeter. So the high fluence light never sees a material optic at this point. And all the noble gases that are where the pulse compression is being done are at atmospheric pressure with shutters and at low rep rate. So it's a relatively simple system. And you can see their progression in time, 3 microseconds, 30 nanosecond, 1 nanosecond on target. And so this point design here is 61% efficient overall from the output of the Caref to light on target. We believe that nth of a kind, in the long run, we'll be able to achieve 72% efficiency with a lot of work. For wall plug efficiency, this gives you, for this point design, 5.2% efficiency from wall plug to target. And we expect to be able to push this to 7% in the long run. Okay, experimental demonstration by our team. So this was an experiment done by our team in the 1980s using a excimer laser to pump a Ramon conversion experiment. Shown on the upper left is the actual laser. That output aperture is a 1 square meter aperture. This is a floor plan of the setup, of the experimental setup. You see this laser in the middle there. You see water lines, that's for electrical pulse compression, because this laser output 500 nanoseconds, not 3 microseconds. And the Marx generators were about a microsecond, since there was electrical pulse compression to then drive the E-beam diodes at 500 nanoseconds. And then the output of this excimer laser was sent around all these mirrors around the lab to pump a Ramon cell, very similar to what you saw how the aperture combiner works, the beam combination coming through, shown down here, where you inject a Ramon seed and you pump it with 2 pump beams crossing it. In this case, there's a telescope. The amplifier has a telescope in it. Beam comes out, expands, so it's a double pass system. And this is an actual picture of a shot that was done. You can see here the aperture combiner, or sorry, not the aperture combiner, the Ramon cell in this case. In this case, the Ramon medium was hydrogen. Next slide. The scattering was done off the vibrational H2 Ramon transition, not rotational N2 transition, but very similar physics. And this is a plot of a lot of the data taken from the system. And so Innovin's team members in the late 1980s were able to achieve a kilojoule output with 50 stage gain from this system at 82% conversion of maximum efficiency. Another key point is that this process was computable. And something I haven't mentioned yet is bandwidth of the light. The bandwidth of this light in this experiment was 150 megahertz bandwidth. So that was shorter than the line width of the Ramon transition. And so that really means you're only dealing with a few waves when you're trying to calculate the process. You know, the seed, the pump, and the medium response. And so this is computable. Then they demonstrated diffraction limited output with 20 poor quality pump beams crossing the amplifier. And the average on-axis pump intensity was 50 megawatts per square centimeter. So a critical experiment that was done is shown here. So here you see the amplifier being pumped by the output from the excimer laser. And it gets telescoped up. But then over here, there was kind of a reverse telescope, and the beam was telescoped back down to the same size as the input. The C beam was injected here. There's a beam splitter. So part of the light went down along this optical path, not through the amplifier at all, over here and up through a beam combiner and hit a view screen. The rest of the light went straight through, went through the telescope up, telescope down, recombined with the light and hit the view screen. So this is like a Mach-Zehnder interferometer. And shown up here, reference with no pump, is the interference pattern of these two beams of different path length showing up on the view screen. So they did a shot without pumping the amplifier. Then they did a shot, the same setup, but they pumped the amplifier with the light out of the excimer laser. And they achieved 500 joule output and 70 stage gain here. But the key experimental demonstration here was that the interference pattern with pump on and pump off were identical. There was less than 1/15 of a wave RMS phase difference between the light. And so this is really key because it means the seed amplification by poor quality pump beams via stimulated scattering does not affect the seed beam quality. It won't impress phase distortions on your light. And remember, these pump beams were traveling all around the lab. There wasn't thermal control. There was poor beam quality. So the key point here is that you can image through SBS amplification, which, as I talked about the final section in the Aspen architecture, when image a pattern on target with a phase plate, light leaves the lens, then it amplifies, traveling through a very low linear and nonlinear index medium. And that amplification process doesn't affect the ability to image. Very key experiment. Okay, so what are some of the limiting physics phenomena for beam combination? Shown here is a depiction of the point design system, lab air, interaction length. Here you see the 18 megajoules coming out. And here you see a shutter, and it goes into neon. Neon is not Ramon active, and that's an important point here I'll mention in a minute. So the first limiting phenomenon you could imagine is breakdown. As you really put the juice to the system, you're going to hit some phenomena that'll make things stop working. Breakdown's an obvious one. If it's too intense, you break down the light, can't propagate, it's a problem. The breakdown intensity, however, of 3 microseconds, quarter micron light is about 10 to the 10 watts per square centimeter. We're well below that, so we're good there. Next is amplified spontaneous emission. So what ASE is spontaneous. It's where light spontaneously scatters in a given direction, and then once generated, that light will amplify via SBS, deplete your pulse, and take energy where you don't want it. And that's not good. And what's called the small signal gain length of the process is what determines how much ASE there's going to be to zero order. The small signal gain length is the dimensionless quantity, product of the coupling constant times the intensity of the pump times the interaction length over which the beams are crossing. Interaction is taking place. And a small signal gain length of 10 is low enough to prevent ASE from depleting your pulse. And of course, so once this high intensity pulse enters neon, if there was a bunch more atmosphere down there, you would start to deplete the pulse from ASE, from the Ramon conversion. But because it enters neon, neon's a monatomic molecule. It's not Ramon active at all, no Ramon scattering. Finally, there are distribution function effects. So the way the Ramon scattering works is, in air, you have nitrogen molecules, and there's a Boltzmann distribution of which molecules are in what rotational state, given by the J quantum number. And this is just the Boltzmann factor shown here. And you can imagine that if when you stimulate scattering, you go from state J to state J plus 2 from selection rules. We go to state J10 to J12. If you really pump your process hard, you can imagine from stimulated scattering depleting state J10 so fast, faster than it can collisionally relax and form a Boltzmann distribution again. And if you deplete your state faster than the collisional time it can fill in, your process will stop. And you can then do a simple estimate of this limit. And again, interestingly, you get about 10 to the 10 watts per square centimeter, and we're below that here. Okay, so physics of SBS pulse compression. So again, shown here, you have a pump beam coming in. There shows the wave vector and frequency. A gas phonon, so density fluctuation in the gas, and then a Steed-Stokes beam coming back at that given wave vector and frequency. And these are the fundamental equations governing the process. Here you see again the Stokes amplifies as it moves along, pump depletes. And the way you model this phenomenon is you use Maxwell's equations to govern the pump and Stokes E field, and you use Navier-Stokes equation to model the phonon. And when you solve these coupled equations in many textbooks, these are the solutions you get for the coupling constant, which is the strength of the interaction. It's a Lorentzian line shape, and that gives you the shift and the line width of the line. Important takeaways here is that the coupling constant scales quadratically with density, and the phonon lifetime scales linearly with density. So what are the equations modeling the backward SBS extraction? It turns out for pulse compression, when the seed pulse is very short compared to the pump, it's the fluence that really matters. So it's the energy per area passing through the system, not intensity. So you see here, basic setup, Stokes seed is injected. At one fluence, it comes out at a higher fluence, and the pump depletes. And it turns out when you solve those equations in this under these conditions, this system behaves as an energy storage amplifier governed by the Franz-Nodvik extraction formula, just like a glass laser, like NIF. Of course, the extraction here, instead of the small signal gain based on the laser transition line, here it's the coupling constant gamma B times the pump intensity that determines the physics. And so this is, again, this dimensionless quantity, this small signal gain. And note that you can also write that in terms of the pump fluence divided by what's called the saturation fluence. So this is a saturating amplifier. It behaves as a saturating amplifier. And the saturation fluence is inversely proportional to the Brion coupling constant. And you can plot the solution for this. Here you see extraction efficiency on the y-axis. That's how much of the pump energy is transferred to the seed beam. And then the stage gain is the other important parameter. The stage gain is what's the amplification of the Stokes seed beam. How much does it amplify? And again, ASE plays a role here. Just like for the Ramon case, you can have spontaneously scattered light that amplifies via SBS and depletes your pulse. And the limit threshold to prevent ASE is about 25, so you'd probably want to operate with a small signal gain length of 20. And so you can see that curve here for a simple single stage extraction gives you the efficiency versus stage gain there. Okay, so let's consider a simple design concept here. We're going to try to design a very simple conventional SBS compressor. So here we have our pump, here we have our seed, we have our SBS interaction medium, there's windows, and we have our output pulse. So requirements for ICF, very generally, nanosecond scale pulse length, 5 joules per square centimeter, because windows have damaged fluence at short pulse. And you also want good gain and extraction efficiency. Here, the pump fluence over the saturation intensity, choosing about 20. And if you go through the numbers, this is an order of magnitude, estimation here. You can calculate that in order to achieve these parameters, you need a coupling constant of 0.3 centimeters per gigawatt. So that's a constraint on the coupling constant. There's also a constraint on the phonon lifetime, which I haven't talked about yet. And I mentioned the line width of the transition. There's what's called the phonon lifetime, which is the inverse of the line width, essentially. And if your seed beam is of order the phonon lifetime or shorter, the equations governing the process are more complicated. You can't drop time derivatives. The Franz-Nodvik extraction formula I just showed doesn't apply anymore. You have transient effects that inhibit the process. You get pulse breakup, reduced gain, and this is discussed in detail by Damson et al. In their paper. So another constraint is you want the phonon lifetime to be much less than a nanosecond, which is the pulse length you want for ICF. So choice of SPS medium. So here are these requirements. You also want low nonlinear index, high transparency, low forward Ramon gain. You don't want Ramon ASE extracting your pulse as you're trying to do Brion pulse compression. And so these are the kind of possible media. And shown in blue are media investigated by Damson et al. SF6, CH4, nitrogen, xenon, argon, and all at 10 atmospheres. And you can see at 10 atmospheres, there's a few potential candidates here, like nitrogen and argon. Their coupling constant is close to 0.3, so there's a few potential candidates. But high pressure, this 10 atmospheres, it enforces the damage fluence constraint, because you have to have windows if you have a high pressure cell. Interestingly, Damson et al. In their paper, they made a comment. They say, it is interesting to note that stimulated backscattering is experimentally observed even in nitrogen at atmospheric pressure. And they quote a paper by Averbach, a Russian, part of a Russian group. Okay, atmospheric pressure makes things simpler. So let's go to 1 ATM. We can go to windowless operation. Now we can drop the constraint on fluence. We don't have windows, and then the constraint on the coupling constant. So we go back to the scaling. Okay, the coupling constant scales quadratically with density or pressure. And so, well, you expect if the coupling constant to drop 100 times, get 100 times lower if you go from 10 atmospheres to 1. However, this is not the case. And this is a critical insight here. So it turns out that the hydrodynamic theory, which as I mentioned, you conventionally used to model the phonon response in SBS, it's inapplicable when the line width of the process becomes comparable to the Brion shift. Another way you can plug in numbers, rework it. Another way to see this is that you have the gas, the molecules are scattering around. If the phonon wavelength is short compared to the mean free path of the gas particles, well, you can no longer use hydrodynamic theory. It's not collisional. You need kinetic theory in this case. And when you go through all the math, you solve coupled Maxwell's equations, Boltzmann's equations, kinetic theory, you ultimately find that in the very kinetic limit, when the phonon wavelength is short compared to the mean free path, that's this y parameter, much less than 1, the coupling constant only scales linearly with density, not quadratically. And so here are some plots of this calculated. You can see here that in neon, which is our medium of choice in this last section that you saw in the fast compressor, that's a very low nonlinear index. At 1 atmosphere of pressure, the coupling constant is 13 times higher than you would expect if you just applied the conventional formula in most textbooks to the process. That's a big difference. The upshot of this is that hydrodynamic theory underpredicts SBS gain at low pressure. Kinetic theory leads to 13 times higher gain at 1 atmosphere in neon. And this parameter space was apparently overlooked. So Innovent's insight is windowless high fluence operation. This eliminates material optics from that, 99.99% of the final pulse energy, because we amplify 10 to the 4 after the rays leave the last final optic of light. We can pulse compress to a nanosecond or less at high fluence. And the upshot of this is we can put over 10 megajoules through under a square meter of cross-section in the system. So of course, SBS has its own limiting phenomena. What limits the process? First, again, breakdown multiphoton absorption. And it turns out in the fast compressor and neon, we're about, and helium, those are the two gases that the very high intensity pulse is coming through. They have very high breakdown thresholds at 1 atmosphere. And we're about an order of magnitude under the curves for breakdown. So it's good. Second is nonlinear phase accumulation. So even though the nonlinear index is very low, it's not 0. And if you accumulate too much nonlinear phase, that can disrupt your ability to project a pattern on target that you want with good uniformity. A typical measure of this is called the B integral. It's just the calculation of what the total nonlinear phase accumulation is along the light path. And typically, if it's under 2, or if it gets above 2, light will have a propensity to self-focus, filament, and you'll have a lot of problems. The B integral in our final section is under 1. And so it's kind of a design constraint for us. And so you can see here's glass. comparing the linear index of refraction, or then -1, and the nonlinear index of refraction compared to neon and helium. Almost 5 orders of magnitude different in nonlinear index. So we can handle much higher intensity at good beam quality than a glass laser system. Finally, SBS, we have found that this is the most limiting phenomena for us. So again, you can imagine, a pulse of length LP, which is the speed of light times the pulse length, propagating across a gas of length L sub g. Shown here are results of ASE for neon. On the y-axis is what we call J1%. So that's the fluence of the pulse at which you'll lose 1% of the energy to ASE. And then the x-axis is pulse length, and the different curves are different propagation lengths. And you can see here, for neon, for a 20 square centimeter beam, your J1% is about right where we're operating, over 1,000 joules per square centimeter. Interestingly, the threshold goes up at shorter pulse length. It's the interesting result there. So we've done extensive 3D ASE calculations, and our ASE loss in our Aspen architecture point design is under 2%. Next slide. Finally, there's also a distribution function effects. If you drive the system really hard, you'll expect to run into them, just like in the Ramon beam combination case. So the SBS process in the calculation of the coupling constant, you typically assume that the perturbation, the acoustic fluctuation in the medium that you're scattering off of, is small compared to the background density, as shown here for the distribution function. However, you drive the system hard enough, that fluctuation will get big, and if it gets too big, this linearity assumption no longer holds. And what happens is you get a reduction in coupling constant, energy transfer to other modes. It becomes a very complex problem. You want to avoid that. And so we've done kinetic simulations for all the noble gases. And shown here is the normalized coupling constant versus what the intensity product. That's what determines this process. It's the pump intensity times the Stokes intensity of the beams. And we operate here just before the curves start to come over, where distribution function effects will come into play. So this is just an illustration of how we envision a future IFE power plant to be based off of the Aspen laser technology. So up here you see, and this is to scale, you see 2 beam lines. One beam line, you probably recognize it, that I've shown you. But then there's a mirror image, counterposed beam line from the other way. And this gives you 2 beams coming in, 180 degrees, which can deliver, in this case, up to 24 megajoules to target. And this just shows a sketch. This is kind of zoomed in. This chamber here is the reactor chamber, target injection, and coolant loops, et cetera. You'll hear more about this from Mike Tobin. So bottom line, what we've strived for is low-cost driver, high single pulse energy, high fluence before focus, and the high fluence is directly related to small solid angle here. So when you're at the target and you're looking back at the final solid angle subtended by the final optics, it's very small because we can get such high fluence effectively by amplifying after imaging in the fast compressor. Large standoff, over 50 plus meters if needed. That really decouples the laser from the chamber. High efficiency, of course you heard that glass has the potential to go to much higher efficiency, so of course this is a trade-off that needs to be investigated in detail and with what target gains can be achieved. But this is the range that we expect for this architecture. And the ability to reparate, the assessment is that a 1/4 hertz doable, under that doable, getting up to 1 hertz will be difficult. Okay, so the next steps. So we've designed in detail a demonstration laser that will validate this kinetic SBS physics and our ASE calculations that we've done. And it'll demonstrate imaging light into a pattern through SBS amplification with a B integral of about 1, same as it will be in the full system. And this will produce a kilojoule output. And here, we'll pump the light at 500 nanoseconds in 1 compression stage, go down to 1 nanosecond. And so this is what we would like to build to validate a lot of the physics. And then finally, in conjunction with that, build a prototype Mark's line and electron beam diode for the large Caref amplifier, which I showed you at the beginning, and begin an engineering initiative for being able to reparate it in the long run. Steps after that would be build a full megajoule module, so the 25 by 25 centimeter optic that I showed you, just one of the 12. Build out one and put megajoule to target and conduct a series of laser target coupling experiments. And then finally would be build out the ignition system. So references, which you saw throughout the talk, and that's it. Thank you.
Okay, great, thank you. I can't help but start by tying in something that was in the first talk this morning. So you saw that photograph of the actors next to the NIF chamber. You saw that earlier this morning? So I was the physicist that helped design that chamber for the NIF. Oh yeah, that's right, thank you. And coincidentally also, I have a 17-year-old son who I'm trying to get interested in science and engineering. He turns out he's going to be a mechanical engineer, so that's good. But for years and years and years, he thought his father's greatest success was he designed the chamber that Captain Kirk died in. So that was my claim to fame. But with that, I'll try to do a little bit better than that in this presentation here today. This is going to be a quick presentation. I think in some ways it's going to be pretty obvious. This is kind of logically what would you try to do to capitalize on this great initiative, I think it's a great initiative about this tubing KRF system. Had a lot of help putting this talk together, and in particular, I want to call out Christophe Debinel, who's sitting 3 back in this row here. He came down from Paris today for the meeting, and he's the true expert when it comes to this FLIBE and FLINE that I'm going to be talking about in a bit. So when we get the hard questions later, I'll let him answer them. Okay. So a very important professor in inertial fusion energy in the US was Jerry Kulsinsky. And in about 2001, he outlined what he thought were the biggest challenges toward mating a driver to a successful target concept. That's injecting the cryo target successfully to chamber center, particularly for direct drive. Cavity clearing rates, because typically something is going to be melted, vaporized, dislodged by the output of the target. And so you have to get back to a virgin condition for the next shot. Neutron radiation damage, which I'll talk about in some detail, and finally capital cost of drivers, which I think has been touched on pretty well before now. So one of the most important things to set the stage for this discussion is what is emitted from one of these targets when it goes off. So most importantly, the neutrons makes up 80% of the net reaction, right? But it's about 75% of the net energy coming away from the target because they're scattering in that dense fuel. So you get a distribution around 14.1 is the highest, and the average energy is more like 10 or 11 when it leaves the target. But it's emitted in less than a nanosecond. Very key point that I'll come back to. Then you have X-rays down on the bottom there. That's about 10 to 15% of the net energy. There's a variable because for thicker, heavier targets, there'll be less X-rays and more debris, so there's a trade between those. That's about 100 nanosecond duration in its emission, about a 300 EV black body. And then finally, the rest of that, of course, is debris, much slower moving, obviously, than the speed of light, or 14 MeV neutrons. And those are tens of microseconds in duration to get out to the wall. So each of these has to be managed, mitigated, in having an efficient power plant operation. One advantage of the target that has been looked at now for this tubing KRF system is this outer layer may act as that insulator from the very hot chamber that could be at 600 or 700 centigrade. And of course, the fuel is at 17 Kelvin to preserve it so that it's not getting, you can't even survive a degree Kelvin increase as it gets to chamber center. So we think that's a big advantage to have an indirect drive type of target. So 50 years of research, as Manolo reminded me last night, there's about 30 different inertial confinement fusion concepts that have been developed. You can kind of classify them into 4 categories. Just a vacuum chamber, maybe put a protective gas in that chamber to slow down the debris, but still allow the beam to get into the target. wetted wall. The Koyo laser from Japan is probably the leading candidate there. So a thin liquid layer at the wall that can intercept the X-rays and debris. But the one we're going to talk about today is the thick liquid wall called high life. And some of the benefits, of course, the liquid has that lithium in it, so you're breeding the tritium very robustly. You're protecting that first wall from that tremendous neutron insult. So you can have an entire lifetime first wall. You're not stopping and rebuilding the reactor basically every 2 years because you're protecting from that 14 MeV fluence. Low activation for the same reason. You're mitigating the neutron insults. Of course, you absorb the X-rays and remove the debris. But again, can you clear the chamber in time? And can you have nice stability of this liquid so that you're not impeding this KRF beam as it goes into the target? So those are the key questions. And I like Christoph's comment here that High Life 2 basically replaces material science challenges with fluid mechanics questions, and hopefully more simple questions than the material science. All right, this is a picture from the Livermore Energy and Technology Review from December 1982, so the original high life concept. So isn't it interesting that as John Knuckles and others thought about birthing inertial fusion, they thought about a two-beam system with lithium as a thick liquid layer to breed the tritium and yet protect the first wall. So in a sense, this KRF system allows us to go back to the future and think about this initial fairly simple approach toward reactor technology. Now, what happened with this from 1975? Well, about 1990, they said, look, we're going to replace the liquid lithium because that's a known tremendous fire hazard. So we're going to put in a eutectic salt, either FLIBE, F-L-I-B-E, or FLINABE. So that's fluorium, lithium, beryllium. And it's a eutectic salt that melts at about, 460 degrees centigrade, or FLINABE at 340 degrees centigrade. So it's helpful that if you're in a condition of shutdown, everything freezes, literally, back to a solid. You don't have an issue of liquids that are being displaced. But as the understanding about what gain you would get from different drive energies, they increased the drive energy from 1.5 to 5 megajoules because the gain was now 70 instead of 800. And they said, and we need to rate the chamber at 6 hertz now in order to have something like 1,000 megawatt electric capability. And then, of course, later, as I mentioned, they put in the eutectic salt in place of the liquid lithium. This, I think, is the most recent concept. This has evolved over almost 150 papers in over 35 years. So there's been a lot of attention and interest in developing this concept. And you can see here that this is assuming a heavy ion beam is the driver, and not just 1 or 2 beams, but in the end, there was 120 different beams that were going to be penetrating the chamber to get a target to work. To me, as I saw this evolution, I thought, this doesn't pass the ho-ho test, as we call it. I don't see how you really make this work. And they had this very sophisticated construction of jets and oscillating jets that forms this main cavity within which to inject the target and bring all these beams in. Again, it looks very, very complex, and I like the original design a lot better. So this is from one of Christoph's papers and some of his work. So here we're setting up the Tsunami Code, as it's called, where we have the target at 0, 0. The red in the picture is this FLINABE or FLIBE. It's either in a jet that's flowing from top to bottom in the chamber, or it's this oscillating, double oscillating assembly to get this pocket for the target to be entered into the chamber. And so the question here is, once the target goes off, can you get all of this vaporized material out of the chamber in time? And so this is showing a progression in Christoph's calculation. I feel embarrassed talking about it when you're sitting here, but so you see the ablated salt here, and then the debris from the target is intercepting the ablated material, so they're colliding, passing through each other. And then you can see here that there's enough space that vapor is breaking out into the vacuum of the chamber and continues to evolve. And this calculation is stopping at about a microsecond. So what this clearly showed is that the chamber would appear to clear within a millisecond or so. So that's good news, that that would evolve successfully. But what about the stability of these liquids in the chamber? So at UC Berkeley, and fortunately Christoph was there to see some of this experimentation, they figured out ways to create very well-structured jets using water. They worked out the correlation, basically, to say these results would apply to FLIBE if FLIBE was used in these experiments. And so you can see from a Reynolds number of 187,000 to 100,000 to 75,000, you cross a threshold where you get nice stability in the jet. So this was encouraging. Additionally, I mentioned these two oscillating slugs, really, of thick liquid to create the pocket to inject the target in. And you can see in that last one where it says shot time, I have a large pocket and there's the new pocket just above it. So it's this repetitive system of creating these pockets in the center of the chamber. Well, can you really do this? So again, they demonstrated this, again, using water, that you could construct what looked like well-behaved beams, or I'm sorry, well-behaved jets that could oscillate in this manner. Okay, and then finally, I didn't really point this out in the description, but having these jets from top to bottom in the tank, basically, of your reaction chamber, and having these two oscillating slabs that gives you space for your target to come in, that's all fine and well, but you still have that region where the beam is being injected into the chamber. So there's nothing between the target and where the entrance to the target is and going back up that beam line. There's nothing to protect it. And so Christoph thought up that these annular vortexes would be a way to be able to do that. And it's very interesting. In the upper right there is kind of basically the nozzle assembly that you inject the liquid at the midline, and the liquid goes into an annular vortex in both directions before it's brought out of the beam line. And so in in the bottom there, you can see a pretty well-behaved vortex that could protect the beam line, also keep the material out of the beam as the laser beams are brought into the chamber. Okay, getting back to neutrons, because after all, that's where the energy is that we want to turn into electricity. So a couple of major points about this different from magnetic fusion. Magnetic fusion continuously produces these 14 MeV neutrons, so they're continuously being deposited in the first wall. But as you know from our description, you're injecting a target, you're hitting it, it's burning, it's releasing neutrons in much less than a nanosecond. And so your first wall is getting a heavy load of neutrons and then nothing for a long time, and then another heavy load of neutrons. And so in a year, because of this, you are irradiating for only 250 milliseconds in 12 months. What happens to a material when you've done an intense loading and then there's time maybe for annealing, we hope, or maybe there's time for defects to accumulate? We don't know the answer to that question right now, but what's key is that the facility that's used to develop materials for magnetic fusion may not answer this question. So it's another big advantage of having that thick material to take the 14 MeV fluence down to more like a fission fluence and use the knowledge about materials from the fission industry. A couple other points. FLIBE is shown here. This is kind of the chamber radius, and this is straight up here because I'm assuming that the X-rays and debris are, of course, stopped quickly in the FLIBE material. But this is showing the deposition as a function of thickness, really. So about 90% of the energy is absorbed in the 50 centimeter thickness. And there will be other layers outside of the main chamber, right? Because you're pumping the FLIBE back up to the top and it's coming back through. So there'll be other regions to collect the rest of that 10%. And this is, by the way, a picture of FLIBE. And it's kind of interesting that at temperature we would be using it, it's a clear liquid. So it's rather interesting that visually you would see the impurities in that, and keeping this pure will be a very key chemistry issue for an inertial fusion power plant using it. These are a couple calculations that Manolo's Institute helped with here. So displacements per atom, if you have that 50 centimeter thickness, it's about 2 per year. We know materials last to 80 dPa or more. So this shows you have that 40-year lifetime of that first wall with this amount of material in front of it. gas production. Okay, it's less than 100 atom parts per million per year. These are the N-alpha and N-P reactions that take place in the material. And again, these are acceptable for material damage rates, basically, for the gas production. And probably at these temperatures, a lot of that gas will escape out of the matrix. And so, again, very important point. We think that the Flibe thickness basically creates a fission spectrum out of the fusion spectrum and may not need at all that 14 MeV research in order to have a material survive in this environment. I mentioned about the tritium breeding. So again, looking at a 50 centimeter thickness, you'll get about 15% more tritium than you actually need. So ultimately, tritium will be leaving this facility somewhere else because you don't want it to build up and store. So it might even be a source of tritium for other facilities. Connor mentioned about the final optics, great description about how that works out at 50 meters. Well, what happens to the target emissions that heads out up those beam lines? Well, fortunately, the X-rays are fully stopped in the same material that's allowing that final pumping and pulse compression back into the chamber. The debris, of course, is stopped in the same material. The mirror and the lens, both if this is a grazing incidence metal mirror or from the silica lens, it can work without annealing over a 2-month period, and if you change those out every 2 months and anneal those, that shouldn't be an issue for final optics protection. Okay, last comment is about cost. So again, Jerry Kulsinsky, going back to that 2001 talk, he put together these percentages and said, gee, the driver percentage up to 37% and the heat transfer turbine electric 34%. Those are where you got to get the cost reduction to make inertial fusion more economical. Well, probably you're going to live with whatever heat transfer turbine technology is available. And fortunately, since this time, we're talking about helium Brayton cycles. So it's nice to know we're not going to boil water from fusion like we've done coal and everything else. So that's a step forward. But if we think about this high life, well, that's 35% using the numbers from 2011 and 26% for the turbine. The chamber is higher because of the pumping power necessary to recirculate the Flibe. But the heavy ion driver is $223 a joule. And as you heard earlier today, the Aspen KRF is about $13 a joule. So it's a tremendous difference. And so this would appear to address Kulsinsky's concern that the driver is now about 6% of total capital costs for the system. And you've heard a couple times today that A to G should be somewhere around 10 in order to have an economical inertial fusion system. So that was developed by Wayne Meyer, a good friend of mine. This is from his paper for the IAEA book, Energy from Inertial Fusion, that Guillermo Velarde at the Institute was one of the editors. And this basically says you can't have a high recirculating power fraction coming, if you're producing electricity and it all goes back to your driver, forget it. You've got to have a small amount going to the driver. But this is also saying that if your driver is 50% or even 33% of your total capital cost, you're going to be too expensive. But we're now down around the 5-10% area, you can see. So an A to G of 10, the curves flatten out and you're in a really nice operating place. And so if there's a target gain of around 150 to 200 and 7% or so efficiency, this would appear to be an economical combination. Okay, so for the future, certainly confirming one, and I'm always optimistic to say look a little beyond 2 hertz chamber clearing and this annular vortex. We want to really make sure that that's going to provide the protection necessary and clearing possible. It seems to me, and I didn't mention this at the beginning, but I've been working on missile defense for the last 15 years, and I'm stepping back to the future myself and looking at things that were previously done. And I'm surprised that we aren't starting to link codes together so that the output of the target gets linked to the Tsunami Code that's predicting the response in the chamber, that's linked to the tritium breeding and the power production. This all should be one code system that is allowing optimization and getting insight into where the next leverage, high leverage areas for research should be. So that's an important thing, I think, going forward. The cost numbers that I've presented today are at least 30 years old. I think those need to get updated. And Mike Campbell talked earlier about artificial intelligence and machine learning. I cannot imagine an inertial fusion power plant, you know, where you're fabricating targets to the micron level, you're injecting them on the fly to the center of a chamber at probably 10 to 50 meters per second, and it's the target that triggers the laser, right? Because it has to be in the right position, it's being tracked, and then the laser fires and has to intercept it properly. And now you're breeding the tritium, you're purifying the loop of the lithium, the fly or the FLINABE. I don't see that being possible without a deep learning, totally automated system, which is certainly feasible to do, but that's something that we should be working on. And then finally, the safety and environmental review of past efforts and looking forward. Okay, and with that, I'm finished. I know I was your last obstacle to lunch, so I'm glad to be done here.
So thank you to Connor and Mike. So is there any question, comment, curiosity?
I have not a question, I have a comment. Thank you very much, really, Mike and Connor. I think this presentation was something that probably you will remind in your lives, because it's touching, it's maybe touching some aspect that why not we could see in the future. We really push for that. I fully agree, Mike, with your last sentence, that it's perfectly possible to believe, technologically with this aspect. Actually, as Mike said, there are groups, small groups, that still are doing experiments with following the beams and the target at the same time with a precision of micron, 1 micron. They are able to do that. And they are able to do target implosion at 10 Hertz with a precision, with the accuracy in the beam point, in the beam hitting of the target of closely at 50% now in 2021. So imagine that with the new technologies that are appearing. So perfectly it's possible to do that. In this case, you have only 2 beams. This is critical. This is, in my opinion, critical. Very, very important for the simplicity of the system. So I really believe, as you said, that this is perfectly possible. And the ideas that Connor presented here are something that you can think, why is not, why was not in the past? Well, some of us know why, but but the reality is that it's possible. It's possible. So I thank you. I thank you really much, very much about that, Mike. This is my comment. Any other comments or questions to this presentation? Well, if not, thank you very much both.